Hello everyone, welcome back to the class of differential equations and the matrices. And we still have a few more topics about the matrices to cover this time. And so for now, we are moving to chapter 5. And specifically, we are doing section 5.3, Eigenvalues and Eigenvectors. Eigenvalues and eigenvectors are for matrices, and they are defined for square matrix. Okay, so A is an n by n square matrix, and also lambda, it is a scalar quantity. A scalar, it is a real number. And then, if any chance, look at this vector v. Let's assume this vector v, it is not a zero vector. Okay, this is a matrix multiplication, right? A times v. And accordingly, well, this matrix multiplication really will generate a vector of the same size of this v here. And this equation essentially it is saying if this matrix multiplication turns out to be the same as the scalar multiplication to this vector, and in some way we can say lambda it is playing the same role like the matrix A. So accordingly, lambda is called as a special value or eigenvalue of this matrix A. And also this vector v, it also plays a role over here. Not all the vectors will have such a situation. So v is an eigenvector corresponding to lambda. Okay, for a square matrix, if A times v turns out to be lambda times v, lambda is a scalar quantity, v is a vector, and then we say lambda is an eigenvalue of the matrix A, and the v it is an eigenvector corresponding to that lambda. And you may wonder if there are such kind of things for matrices. So I do have a simple example here. This A, it is 2 by 2 square matrix, and actually I'm giving 2 lambda values, and I'm giving 2 eigenvectors, because you want to give a quick check if you are convinced. I'm saying if you do a matrix multiplication A times v1, it really will turn to be the same as lambda 1 times v1. So accordingly, we say lambda 1 is an eigenvalue, and the v1 is an eigenvector corresponding to lambda 1. And similarly, I hope you do take your time, do a verification, do a matrix multiplication to see if you are convinced this is true. A times v2 is the same as lambda 2 times v2. So accordingly, we say lambda 2 is also an eigenvalue, negative 3, it is also an eigenvalue. And this vector 1 and the negative 2 is an eigenvector corresponding to this eigenvalue negative 3. Eigenvalues and eigenvectors. And I guess it might be still very confusing. Pretty much I started this matrix from nowhere. The only thing I can tell here is it is a very well prearranged example. Just want to show you there are such things, eigenvalues and eigenvectors. And then the real question is how do we find out the eigenvalues and the eigenvectors? Well, to find out the eigenvalues and the eigenvectors, we really start from the definitions. That's all the definition we have. AV equals lambda times v. Roughly, you can consider, as I said, lambda plays the same role like a matrix. It is special value, right? It is an eigenvalue. And then, starting from here, it may not tell a lot. It's very hard to figure out what kind of vector or what kind of eigenvalue we may have. So somewhat I rearrange the equation. Remember in math, like I solve those very simple equations, usually we make one side of the equation 0. So I'm trying to do the sign. And then one thing I recognize here is, well, we can say this vector v is a common factor, right? vector v is a common factor. It is. But anyway, when you want to take it out, when you to factor it out, you want to be very careful. If you just factor out this v directly, we are going to have a minus lambda, right? Remember, A is a matrix. Lambda is a scalar quantity. Basically, there's no such thing, a minus lambda at all. But remember, we do have a special matrix. It is called as an identity. So this is the identity I'm talking about. Identity, it is a square matrix of the same size and such that all the elements along the diagonal line are ones, and then anything else, they must be zero. That is an identity. And also, we didn't mention identity plays a role like number one. Okay, you multiply a matrix by an identity to the left or to the right, it will really not change the matrix at all. And certainly vector v, it is a special matrix. It is a matrix. So I could add for the lambda times v part, I could insert an identity here, because the result really will be the sign. The result really will be the sign. By inserting this identity over here, now it makes perfect sense to factor out this vector v. V is common to both. And a minus lambda I makes perfect sense. A minus lambda I makes perfect sense, right? And then the next part, you may want to understand that this v is supposed to be a non-zero vector. It has to be a non-zero vector. Basically, we are solving a system. Well, we are solving a system. We are solving for v from the system. But the v, it is non-zero. Okay, v is not zero, which means the matrix over here, A minus lambda I, it's the coefficient matrix. It must be singular. Anyone remember what is a singular matrix? A singular matrix, simply it is a matrix such that the determinant is zero. And it is only in the case when this determinant of this coefficient matrix is zero, okay, and then we would have a non-zero vector v over here. Otherwise, if this determinant is not zero, which means the matrix is invertible, that means this v has to be zero. Because of the requirement v cannot be zero, so really we are reached to the conclusion the determinant of this coefficient matrix must be zero. And indeed, we call this as the characteristic equation of the matrix A. And also think very carefully, can you tell what is a characteristic equation? I say it is a polynomial equation. It is a polynomial equation. So basically, this is a polynomial equation. As long as we can solve the polynomial equation, we should be able to solve for the eigenvalue, the lambda here. Lambda, it is the root of the corresponding characteristic equation. That is the way how we find out the eigenvalue. So I listed the 3 steps. Basically, I just took those steps from the textbook. Okay. So in order to find out eigenvalues and eigenvectors, and first we will have to consider the characteristic equation. It is the determinant of A minus lambda I. This is the characteristic equation. And then you want to solve the characteristic equation for eigenvalues, because I hope you remember, you note, this characteristic equation, it is a polynomial equation. It is just a polynomial equation. Okay, so we can solve this solve for lambda from the polynomial equation, the lambda values or the eigenvalues. And certainly, sometimes you may only have one eigenvalue, or you may not have. Well, well, you will always have eigenvalues. I meant to say eigenvalues could be real numbers, also could be complex numbers. But anyway, for our consideration, we are just considering real valued eigenvalues. And then last step, what about the eigenvectors? And then for each eigenvalue, remember how we get this characteristic equation here? We are really having a system, right? So we look at the system again. I use notation lambda I because the textbook there, mostly I just say that's lambda. Okay. But anyway, I'm trying to follow the textbook closely. So this equation, it is really the same equation we are considering. Using lambda I guess the textbook just want to emphasize for each eigenvalue, there must be some eigenvectors. And so you solve for V from this vector equation, or really this is a system of equations. There are 3 steps to find out eigenvalues. Step 1, step 2, step 3. How about let's take a look. As I said, the first example I started, pretty much it's from nowhere. How do we know lambda 1, lambda 2, and the V1, the V2? So let's take a look. How we find out, let's say, if we are only having this matrix, how do we find out lambda 1 and lambda 2? So this is really the first example on the textbook. Example 1, and we are having the matrix, and we want to find out the eigenvalues and eigenvectors. Eigenvalues and eigenvectors. So the solution, basically this is really for step 1. I'm putting here step 1, and we consider the characteristic equation A minus lambda I, and A is right here. Basically, this matrix, okay, this is a matrix. You really don't have to change all the numbers. You only have to change the elements along the diagonal line. I, it is an identity. So A minus lambda I is 1 minus lambda, and then the other diagonal line element, it is negative 2 minus lambda. Each element around the diagonal line minus lambda, then the other numbers really stay the same. And then remember I said that this is a matrix, but anyway I have 2 vertical bars for the matrix. That means the determinant of the matrix. Okay, this is 2 by 2. Hopefully determinant is very simple. I consider the cross product, well, the forward diagonal line minus the backward diagonal line. And then you use the FOIL rule, and also you want to combine with this negative 4, the number in the end. So I get a polynomial, right? A quadratic polynomial. And then it can be factored, actually. It can be factored. And the characteristic equation, it is by setting the determinant equal to 0. So we are having a quadratic polynomial. The quadratic polynomial equal to 0, and the quadratic, it is factored. So this is how I get 2 lambda values, 2 eigenvalues. There are 2 eigenvalues. And also it's worth to mention, in general, for a 2 by 2 square matrix, there are 2 eigenvalues. And then accordingly for 3 by 3, there are 3 eigenvalues. The thing is, again, you need to understand the characteristic equation. It is a polynomial. So in general, we say a quadratic polynomial may have 2 solutions. A cubic polynomial may have 3 solutions. And also, speaking of the polynomial, you may want to know we could have complex solutions. And also, in some cases, we could have, a solution with multiplicity 2, and those kind of situations also could be multiplicity 3, those things. But anyway, for now, we will work with the real valued eigenvalues. Step one, actually, maybe just say this is step 2. solve the eigenvalues and the eigenvectors. And then step three, really, I think I say this might be the most complicated, because you really need to look at each eigenvalue one by one. So for lambda 1 equals 2, we got 2 eigenvalues, and then we will have to look at each eigenvalue one by one. I'm just starting from this 2, and then remember, we consider this a minus lambda I times v, a minus lambda I times v. This is lambda sub I just want to say this for each eigenvalue, okay? So a minus lambda I, it is always in the fashion in the matrix like this. And when we lambda, it is replaced with 2. This is 1 minus 2, so that's negative 1, 2. And 2, negative 2 minus 2, that's negative 4. So we are having an equation like this. And I hope it's pretty easy to see. Look at the coefficient matrix. Okay, I'm saying the second row, it is the scalar multiple of the first row, right? So indeed, we can make the second row easily 0. Second row, indeed, it is 0. It doesn't matter. It is a 0 row. It is really equivalent to the first row. Okay. And then what I'm seeing here is this vector must be a 2 by 1 column vector, right? So that's v1, v2. So as I'm saying, this second equation really doesn't matter. It's the same as the first equation. So from here, I just say v1 must be the same as 2 times v2. v1, v2 are the corresponding elements, okay? And also be sensitive about the notation I use. And what I use is v a lot. V with an arrow, that is a vector. And then v1 without an arrow, that is scalar. Okay, I'm saying v1, v2 this time, they are the components of the vector. When I have vector, I always have an arrow on the notation. And even sometimes I may use the same notation like those v's. They are different things. Okay, so v1 equals 2v2 will solve the entire system. And simply we can take a v2 as 1, and then v1 would be 2. And v1 equals 2 and 1 will solve the system. It will meet the requirement of the definition of eigenvalues and eigenvectors. Remember, this is the definition of eigenvalues and eigenvectors. As long as this is true, and this is true, this is equivalent to a minus lambda I v equals 0. So the eigenvector we just solved here, 2 and 1, it is an eigenvector. And also I want you to know any scalar multiple will solve this system, because this is a system of one equation with 2 unknowns. So there are always many solutions, which means for a given eigenvalue, there are always many eigenvectors. And indeed, in this case, any scalar multiple of this vector would be an eigenvector. But anyway, just to simplify the discussion, I'm saying this v1 is an eigenvector corresponding to the eigenvalue 2. Let's just finish this example before we take a break. And we do have another eigenvalue, lambda 2 equals negative 3. So we are starting from the same equation again. I hope you remember this equation really means AV equals lambda V. A times V equals lambda times V. And again, if you plug in negative 3, you will see the coefficient matrix. It is always in this fashion, right? A minus lambda I. Okay, so when we have the lambda 2 as negative 3, this turns to be 4, 2. And this turns to be negative 2 plus 3, 2 and 1. So we are having the coefficient matrix like here. And I still suppose you recognize the first row really it is the multiple of the second row, which means really we are only having one equation here for the system. And which means we are really having many solutions. So I started from the second equation. So I said that T2v1 is negative 2 times v2, right? Because from this line, it simply says 2v1 plus v2 is 0. So 2v1, it is negative v2. And then you can make the arrangement. You can say maybe v1, it is 1, and then v2 will have to be negative 2. And that is an eigenvector corresponding to lambda equals negative 3. Lambda specifically, it is exclusively used to denote the eigenvalue of a matrix. Okay, V, it is an eigenvector. And also, indeed, you really need to know for a given eigenvalue, there are a bunch of eigenvectors. And usually, we just need to identify one. So any scalar multiple of this is an eigenvector. And I just want to make sure we do have one specifically. So I just say 1 and a negative 2 is an eigenvector corresponding to negative 3. Hey, thank you for watching. And the next time we will work on a little more about eigenvalues and eigenvectors.